whenever it dings. All right, so good morning, everyone. Before we get started on this warm-up, while you're working on this, I wanted to make a couple announcements. I found out that they are allowing students on campus for after-school tutoring. You just need to check in with me on what days you want to come, and I can schedule a 1-hour block of tutoring with you in person. You just need to answer a couple of questions on they have like a Google form that you answer saying, do you feel nauseous? Do you feel feverish? Do you have a cough? You just have to, be honest about it and answer no to them. If you answer yes to any of them, they won't let you onto campus. So yeah, that's how that's going to go. So I'm only allowed to have 14 students max at a time, and you can't come in late. So they're giving us 2 hours block from 3 to 5 after school. And I'm thinking of breaking it up into 2 1-hour blocks. So a 3 to 4 session and then a 4 to 5 session. But it'll technically be like 3:10 to 4 and then 4:10 to 5 because I have to personally walk to the front of the school to let you in. Security will not let you in unescorted. So I have to come get you at the front, walk you to my classroom. So that's why you can't be late. So instead of doing 3 to 5 and just doing a 2-hour session all the way through, I'm deciding to break it up into 2 1-hour sessions just in case you end up, knowing that you can't make it to the 3 o'clock session. So if you sign up for the 3 o'clock session and you're late, you can't just hang around and hope that you can get into the 4 o'clock session because people will sign up for the 4 o'clock session. And if it's full, you risk not being able to get in at all. So yeah, I'm going to set this up. I'm going to start this off next week on Monday. Monday, I have meetings until 3, which is perfect. So after 3 o'clock, we'll set up our first after school study session next week. I'm thinking Monday. I don't think I have to rush home to do anything on Mondays. I hope not, but if I do, I'll let you guys know. But I think it should be good. Monday will be the first one. Will you have some online? No, the online stuff will still just be during office hours. So the office hours will be from 1 to 2. Yeah, and that will be the case. Although, would you prefer to do tutoring sessions online? We could do that, but then it's like the same thing as my office hours, pretty much. But we can try. I can set aside a day if you want to do that, and we'll just do we'll just do a study session online. Oh yeah, office hours will still be there. Office hours. This does not affect office hours. You can still come to my office hours from 1 to 2, but on Tuesdays to Fridays still. But the in-person tutoring, right? I think it will be a very nice hands-on approach for those of you who kind of miss that. It'd be nice to actually see you in person. They will require you to have your own PPE. They do not provide masks, so you have to come with a mask, and then I'll have a sign-up sheet ready to go by the end of this week, so I can see how many of you guys are interested in coming on Monday on the first day, and then yeah, that's going to be pretty much the idea. You're going to show up. You sign up if you want to come up at 3 or if you want to come at 4. At 3 o'clock, I'll go down, pick you guys up. I'll wait for about 5 to 10 minutes. If you don't show up by 3:10, we take you upstairs. And if you're late, then you just miss out on that session. If I come down, I have to bring everyone down from the 3 to 4 o'clock session when you leave. And when I pick up people for the second session for the 4 o'clock session, if there's space, if it's not to full capacity and you want to hang around for the second hour, you can. And yeah, that's going to be how it's going to be set up. So that's the good news, right? In school tutoring sessions, so we can start that up next week. So I'm dedicating this to only my AP classes. So it's you guys and my BC class, because it's limited to only 14 students per hour or per in the classroom. So if there's 14 students at the first hour, after the first hour is done, I have to kick everyone out. And then we go back downstairs, see if there's 14 for that one. And then we'll have to do like a random, I don't know. I haven't decided how we're going to pick who wants to stay for that extra hour or not, if there's extra spaces. Okay, so that's the gist of it. I will be on campus starting next week just for this. I did not know that this was available. This was an option for us. I did a really poor job of checking emails, so we could have started this this week, but yeah, that was my fault. I kind of dropped the ball on that one. So we'll start it up next week, and then this is perfect. And then hopefully we can wrap up our last 2 units, and then next month we'll start reviewing for your AP exam. It's coming up soon. Your AP exam is going to be on May 24th. On May 24th. Okay. All right. So that's that. If you have any questions, let me know. If you have any concerns, let me know. Everything else will still be running the same. I'll still be lecturing like normal. You still come into this Google Meet like normal, but the tutoring is just extra, right? It's just extra. So if you want to show up, if you have any questions, if you have any concerns about any of the topics that we've covered, or you need some more practice, and you feel like online isn't helping too much, we have an option now for in-person tutoring. So just letting you know. All right. So let's jump into this problem right here. We have here the integral of 18x squared over the quantity 2x cubed plus 1 raised to a power of 4, right? Now, I kind of gave this away that we're going to be using U-substitution, right? But hopefully when you look at a problem like this, right, you remember there's no division property for integrals, right? I can't just take the integral of I can't take the antiderivative of 18x squared, whatever that is, right? I think that's going to be like 6x cubed, right? And I can't just divide that by the antiderivative of 2x cubed plus 1, whatever that's going to be. I can't just divide those two. There's no division property for integrals like that. We can't just go ahead and do that. Even though we know, like, addition property works, that doesn't mean the division property works, and it does not exist, right? And we learned that when we took derivatives, right? When we had a function divided by another function, you guys remember we had to learn this property called low d high minus high d low over low low, the quotient rule. There's no quotient rule for integrals, right? It doesn't work as easy as derivatives do. So undoing things get a little bit messier. So we use this technique. We call it the U-substitution method, right? Some places just call it the substitution method. I like calling it the U-substitution because I actually don't know. It's just old school, I guess. All right, so check this out. First step, right, when you're doing U-substitution is to see if one of the factors looks like it's the derivative of the other factor, right? And I'm hoping you can see that. X squared definitely looks like a form of a derivative of x cubed. You see that? If I take the derivative of x cubed, I'm going to end up with something x squared, 3x squared, right? Or 3 times 2, but you get up with that x squared. The numbers as the coefficients don't match up, but that's okay. I'm hoping that all the variables with their powers match. It doesn't matter if their coefficients don't match. We fix that by, solving for dx and substituting and seeing whatever coefficients we end up with. So this is what I'm saying here. If you see that x squared is a factor, that factor of x squared is a form of a derivative of the other one, which is the x cubed, we're going to let u equal to the form that is not the derivative, which is 2x cubed plus 1. That's what I'm going to let u equal to. Okay? So I'm going to pause there for a second. Are you guys okay? Are you guys okay with that? Does it kind of make sense why I let that equal to that? Do you have any questions or concerns on why I let u equal to that? And here's the beauty of this. If you end up letting u equaling to the wrong thing, right, it's not the end of the world. You just go back and let u equal to the other thing and you try it. And I don't know why, but most students hate that. They want to get it right on the first try. And that's not what math is about. It's okay to do some trial and error and get the wrong choice. And that's actually going to happen more often than you think. And you got to get comfortable with that. You got to get comfortable with that. Anyways, I'll show you what I mean when we go on to the next problem. But let's go right here. We're going to go ahead and once you get u equal to something, the next step is to take the derivatives of both sides and write them as differential equations, right? Instead of writing it as du over dx is equal to 2... The derivative of this is going to be 6x squared, right? Instead of writing it like this, du over dx, I'm asking you to write it as a differential equation. It's du and then have the dx over here. Have all the x's and dx's on one side and all the u du on the other side. It's just going to make it easier for us. That's all it is. It's basically a shortcut I'm trying to show you guys here. Once you get the du, the next step is to isolate the dx. Get the dx by itself. by dividing both sides by 6x squared over here. Divide this by 6x squared. You end up with du over 6x squared is equal to dx. So I have some stuff to sub out now, right? I have this dx right here I can substitute out, and I have this 2x cubed plus 1 I can sub out. So I can rewrite this integral as the integral of 18x squared over, and in parentheses here, instead of 2x cubed plus 1, it'll be u raised to the power of 4. I'm replacing the dx with du over 6x squared. So we're almost done with this, right? We're almost done with this. We got to this step right here. And again, when you're substituting out your stuff, you're hoping to get rid of all your x's, right? You're hoping to get rid of all your x's, just like we talked about yesterday. You don't want your x's in your life. It makes it complicated, right? So right here, you'll notice that the x squared and this x squared will cancel each other out. The 18 and the 6, you can even reduce that. 18 and 6 will reduce down to just a 3. So what I'm going to be left with here, I'm left with the integral of 3 over u to the 4th. It's horrible writing there, right? 3 over u to the 4th du. Now, I know this doesn't look as clean as you want it to be, but it's cleaner than where it was to start with, right? It's a little bit easier to deal with now. There's a couple things I'm going to do in one go right here. I'm going to take that 3 as a coefficient. I'm going to write that out in front. So I'm going to write this as 3 times the integral of 1 over u to the 4th du, right? And then the 1 over u to the 4th, I'm going to rewrite that as a power without any fraction form. So it'll be 3 times the integral of u to the negative 4 du. And we want to write it into this power form because remember, there is a power formula for integrals, right? The power formula for integrals, does anybody remember it? What's the power formula? Let me write this out. This is going to be our side note. For the power formula, if I have the integral of u to the n du, right? What's the power formula? Oh yeah, x works. It'll be x to the n plus 1 divided by n plus 1. So this will be u to the n plus 1 divided by n plus 1. And I can apply that to this integral right here. It might not be an x, but it's still a variable, and it applies the same way. So this is going to be equal to, also, there's a coefficient in front that's just going to be multiplying with it. So this will be 3 times u to the power of negative 3, right? Because the power rule, right, is plus 1. So over here, right, it's going to be negative 4 plus 1. It'll be ending up with a negative 3 divided by that same power. Divided by that same power. Also, don't forget, of course, there is a plus c on this one, all because that integral has no limits, right? It has no a or no b. It is an indefinite integral. We have to make sure we include that plus c. And we're going to talk about a little bit more about that plus c today when we go over slope fields. I was supposed to make a video of slope fields and make you guys watch that on your own time, but I feel like I'm overwhelming you with work, especially with those of you who want to boost your grade. I got to make this plug every single time. For those of you who want to boost your grade, Khan Academy is your opportunity to do so. If you haven't made an account on Khan Academy yet, I put the first assignment up. It's like 89 assigned things, and that seems very overwhelming, but 80 of them are just videos, and you don't have to watch all the videos. I'm putting up those problems there for you to practice, and I want you to watch the videos if you feel like you don't understand it. And I'm going to be using, basically, if you watch more of the videos, though, I can see that you're interacting with it more. But I'm going to be using that to help boost your test scores even further. I haven't finished calculating your curves yet for those who did the Delta Math and those who did the review. Your test scores that you have on Canvas, that's just your raw score, by the way. That's not how it's going to go into your Power School grade. I'm going to curve it first, and once I curve it, I put that in. If you look onto Khan Academy and you do those assignments, before Wednesday, I will help push your grade a little bit higher up as well based off of that. Anyways, I'm getting myself sidetracked again. But come back to this problem. You're almost done with this problem, by the way. You're almost done with this problem. You can simplify it first before you actually resubstitute back in here. This 3 I can distribute. And when I distribute this 3 into here and here, I end up with this 3 canceling out with that negative 3. I end up with negative u to the negative 3rd plus 3 times c. That's still a constant. I'm just going to leave that as c. Constants are interesting, right? You could write it as 3c if you really wanted to, but it's not that big of a deal if you don't. It's just a constant that's there. Okay? We'll figure out what that constant is later. U, on the other hand, is something that we let equal to something else. So I'm going to substitute that back out. My final answer is going to be negative. And instead of u, I'm going to write in here, it's going to be 2x cubed plus 1, right, raised to the power of -3 plus c. And this would be my, if this is a free response question, like my tests usually are, I'd be happy here. I'd be happy here. If you were taking a multiple choice test answer would probably look something like this. It will probably look like -1 over 2x to the third plus 1 to the third power in the bottom here plus c. Like I said, free response question. I love leaving it like this. I don't have to do the extra work. I've already substituted back in. Multiple choice question, they'll probably write it like this because this is the more proper way. How do you feel? You doing okay? U-substitution is a very odd and strange one to look at, especially when functions get way out of hand, and they do get way out of hand, and they get way out of hand very quickly. But hopefully you're okay with that. Hopefully. Does it seem okay, or is it very what do you guys think? You're not okay, you are okay, you don't know how you feel. Can someone type into the chat? Just let me know. What do you think? How's it going? Are you guys still alive? Are you guys still there? It's a bit tedious. Brian, I agree with you. It is a bit tedious. It is a very tedious way. David, you're A-okay? All right. Sounds good to me. Sounds good to me. Okay, let's do some more problems. Okay, let's do some more problems. So this one right here. Let's go ahead and try this one out and see how you feel about this. This is where it gets a little wonky. You ready? Let's take a look at this one. Let's say I was trying to solve the integral of sine to the 10th power of 3x times cosine of 3x dx. Right off the bat, a lot of students will look at this and just give up. And I don't know why. Actually, that's not true. I do know why. It looks daunting, right? It looks hard. And most of the times when things look difficult, you kind of just don't want to try, which I don't know why that's the case. You know, I feel like it's fun to have a challenge. It's boring to have things that are easy, right? If it's something that's just something you just know how to do right away, like, why? You know, I don't know. Maybe that's just me. I like looking at a challenging problem and trying to tackle this challenging problem. So for right now, right, I know that we haven't learned a product rule for integrals. We know a product rule for derivatives. You know, derivative of the first times the second plus the derivative of the second times the first. We'd have our derivative done and we'd be good to go. This is, of course, is a product rule, right? I mean, this is a product of two functions, right? You can see it right there. You can see it's a sine function multiplying with the cosine function, right? With 3x inside both of them. So, excuse me. I can't take the integral of this straight up. There's no rule that will help me to take the integral of sine by itself and then take the integral of cosine by itself and then multiply them together. That doesn't work that way. So we're going to go ahead and try U-substitution, right? We're just going to try it. And we're going to let U equal to, and I'm going to pause here for a second. Somebody have a guess or an idea of what do you think we should let U equal to in this problem? What should I let U equal to? What do you guys think? Sine of 3x. Monica is going with that. We're going to go ahead and try that. And if Monica is wrong, right, what are we going to do? We're all going to get angry at Monica and blame her for this problem. That's right. That's right. And so it's not Mr. Nakami's fault. It will be Monica's fault. That's a good way to go with this. So it's not that big of a deal is what I'm saying. If it's wrong, we try letting U equal to something else. Okay? A common one that most students try to go with is the most innermost function. A very common one is trying to let U equal to 3x. And we'll look at that afterwards. Even if this works out, well, I'll show you why. Or would it be sine of x? I can't let U equal to sine of x because it wouldn't replace anything, right? It would not replace this right here. So if I let U equal to sine of x, it's not a bad idea, but it just won't replace this, right? Sine of 3x and sine of x are not the same, and I can't just take the 3 out of the sine function. It's not like this, right? If I had 3 times x plus 9 and you could factor out a 3, right? Sine doesn't work that way. Sine of 3x is just sine of 3x. You can't factor out the 3 from the sine function, right? because it's on its own. Just like the ln function or the log function, you can't just factor those things out of those things like that. So I think this is a good choice, Monica. It's a good choice. Sine of 3x is a good choice. I was just teasing you, right? So let's just try it, though. Let's see what happens when we let that occur. So if I take the derivative of both sides and get the differential equation, right? I'm saying differential equation because it's an equation with differentials. That's what this d represents right here. And I'm not doing it as du over dx, right? But let's do this over here. What's the derivative of sine of 3x? Derivative of sine of 3x, I need to chain rule this thing, don't I? I need to chain rule this. Derivative of sine is going to be cosine of 3x. Well, what's the derivative of 3x? Right? We have an inside function here. We have an outside function. The inside function is 3x. The outside function is sine of some stuff. I have to do the derivative of both. Derivative of sine is cosine of that same stuff. Derivative of 3x. Help me out here. Help me out here, guys. What's the derivative of 3x? 3. That's right. Again, we're doing it as a differential, so not as a derivative of both sides with respect to x like this, right? We're doing it as a differential to make it easier on our substitution. So instead of du over dx, I'm going to write this as du on one side and dx on the other side when I take this derivative. I know it seems weird, but it just helps out just a little bit more. Just a little bit more. All right. Once I get to this step, I'm going to solve for dx, right? By solving for dx here, that means I need to divide by 3 cosine. That's not cosine. 3 cosine of 3x to both sides. So divide that side to here and divide that 3 of cosine of 3x over here. And I end up with du over 3 cosine of 3x is equal to dx. Now I haven't actually substituted anything back in yet, right? These first few steps are all the same. You let u equal to a function, take the derivative of that, get a du equals to some stuff, solve for the dx that's there. Once you do all that, then we go back and try to substitute everything back in. All right, so you ready for this? I'm going to replace this dx right here with du over 3 cosine of 3x. That's going to be that one right there. I can't replace the cosine of 3x because I don't have anything that's equal to that. So I'm going to write that in like normal. Cosine of 3x is just there. Now, I need to replace that sine of 3x with u. You see that? I'm going to replace sine of 3x with the letter u. So this is going to become the integral of u. Right? I'm replacing that whole entire sine of 3x with the letter u. What needs to go around the parentheses there? What is around the sine function? It's raised to a power of 10. That's right. It's raised to a power of 10. So it's sine of 3x to the power of 10. I'm replacing the sine of 3x with a u, so it becomes u to the power of 10. U to the power of 10. All right, let's do some cleanup here. I don't know if this method is nice enough yet until I see that all of my x's are gone from my life, right? So that's the goal that you want here. You want all your x's to be gone, or all your original variables to be gone with what you replace it with. So I'm replacing here, and I take a look here. Hey, look at this, guys. Cosine of 3x, cosine of 3x, they're the same. I can cancel this out because this is in the denominator right here. That's in the numerator, and I can go ahead and rewrite this. Since that cancels out, this is going to become the integral of u to the 10th, right, times du over 3. That's messy. I don't like it like that. Hold up. I'm going to write it like this. U to the 10th over 3 du, right? That's where that 3 is. Actually, it doesn't really matter, huh? If I put the 3 over here or I put the 3 over there, I could put it over there. I'm putting it like that just because it looks a little bit nicer like this. But if you wrote it like this is perfectly fine as well. But yeah, I like it over here. I like the du on its own there. Now, this is a little bit easier to integrate, right? The over 3, you know, there's a technique. I can take that over 3 out and rewrite this. Hopefully you guys are able to see this. This is technically the same thing as 1 over 3, no, 1 over 3 u to the 10th du, which means that 1 over 3 is the coefficient. I could bring that out because there is a coefficient property for integrals. The coefficient property allows me to take out that coefficient and just deal with the integral on its own, which looks like that. And again, power rule, guys. Power rule comes into play. If you notice the hook or the gimmick of U-substitution is to convert it into something where we can just do a simple power rule on this thing, right? So this right here is going to be 1/3 times the antiderivative of u to the 10th will be u to the 11th divided by 11. Right? Because again, power rule, we just add 1 to the power and then divide by that new power. Don't forget, of course, there's no numbers here for your a and your b for your integral, so you need to also include a plus c. I don't know if you guys have ever seen math memes or not, but I'm hoping some of your math memes are starting to make more sense when you do. It's a random thing to ask from you, but you'll probably notice it now. If you end up coming across some, you'll start seeing things, and it always says to include this plus c. You'll see it. I promise you. It's one of those things that is just like, oh God, oh no, now I understand that. Am I a nerd? Yes, you are. All right, distribute this 1/3, and you'll end up with 3 times 11 is, well, first of all, we get u to the 11th over 33, right? Because 3 times 11 is 33, plus 1/3 c, which is still just c. We're almost done. We're almost done. We're almost done. Right here, we're going to finish this off. This is going to become u was originally equal to sine of 3x. So I'm going to replace that right there. Sine of 3x. But of course, this sine of 3x is being raised to the power of the 11th power, being divided by 33 plus c. And that's it. That's your answer. If this is a free response question, I would be perfectly happy with this right here. Again, if it's a multiple choice question, they do some like small algebraic expression changes, and it could be a few things. Please note that a trig function, right, being raised to a power is the same thing and written like, it can also be written as sine of that power of x. And you saw this earlier in the problem, right? Sine to the power of 10 of 3x. So that's one way they can do it. So in the free response, in the multiple choice answer, instead of writing it like this, they might write it as sine to the 11th power of 3x. Don't get fooled by that. Second thing they like to do, they don't like writing fractions like this if there's no variables in the denominator. If you have an over 33 like this, for some reason, they like writing the something over 33 as 1/33 in front of your problem, multiplying with this trig problem, and then putting a plus c at the end. And this is what it might look like in a multiple choice response, just to get yourself used to that. So if it doesn't look exactly like your work, please understand that they just do a little bit of algebra tweaking to it to get it to look like that. So that's what happens on these problems there. Okay. What do you think? It's a lot. This is what I think you're thinking, right? It is a lot. U-substitution takes a little bit more work, but it's the same work. The hard part is figuring out what you let u equal to, right? And once you figure out what you let u equal to, it's not too bad. It's not too bad. At least I don't think it's too bad. All right. Let's have you take a look at one more before we go on here. Let's have you take a look at one more here. And then I'm going to have you guys try a couple on your own. So let's take a look at this problem right here. So let's take a look at this one. For example, let's say I was asking to do the integral of 1 over cosine squared x dx. 1 over cosine squared x dx. Ooh. What do you think about this problem? What do you think about this problem? Any ideas? I'm going to pause here for a second, let you write that down, and what comes to mind when you take a look at this? All these other problems, right? We've been looking for 2 factors. Sam, confusion. That's okay. It's okay to be confused. You know, it's usually how you learn. You start off confused and then you get shown a solution. And hopefully you learn off of that, but it's rare. It's rare to learn that way. You know, when a teacher gives you the solution, it makes sense, but you don't actually learn anything. You were just spoon-fed it. So, but this one's going to be a tricky one because all the other problems, you kind of saw another factor that looks like a derivative of that. And when we look at this, we can definitely say like, derivative of cosine is going to be negative sine. I don't have a negative sine factor in this one. So it probably won't cancel out if I do it. Right? So what do you guys think? Do you think U-substitution is going to work in this problem? We don't have another factor that looks like it's a derivative of another factor. What do you think? Is U-substitution going to be a method that will help us on this problem? Not really. If you look at every other example we've done, even this one, this monstrosity of a problem here, right? Cosine and sine were derivatives of each other, right? Those factors were. This one right here, x squared, x cubed, derivative of each other, right? Earlier on the other notes, 2x, even 2x has a factor of, has a derivative of 2, right? Even 2x looks like a derivative of 2, right? So coming down to this problem, you know, we're learning about U-substitution, but we also have to take into account U-substitution isn't always the solution. In fact, when you go to Calc 2, which I hope most of you do go to Calc 2 or go to Calc BC, you'll know that U-substitution is only the beginning. There's other techniques that we'll need. In this particular problem, though, we don't need any real techniques. We just need to be a little bit clever. Just a little bit clever. Does anybody know what 1 over cosine is equivalent to? Does anybody know what 1 over cosine is the same as? Instead of writing it as 1 over cosine, we could try rewriting it. Does anyone know what 1 over cosine is the same as? What's the other trig function that 1 over cosine is equal to? Any clue? Any ideas? It's one of the non-common ones, by the way. It's not sine, it's not cosine, it's not tangent. Does anybody know what 1 over cosine is equivalent to? Anyone know what that trig identity is? Anyone at all? Anyone at all? 1 over cosine. Secant. That's right, Brian. That's right. 1 over cosine is actually the same thing as secant x, which means that 1 over cosine squared can be rewritten as secant squared x dx. And you'll say, that doesn't look any better, but there's a few of you, or maybe more than a few, there could be a couple of you, who recognize this. Does anybody recognize this? Remember, the integral is asking you for the antiderivative of this, which is basically saying, what was the original function when you took the derivative of it to get your answer? And David and Monica have caught on already. The integral of secant squared is tangent, because the derivative of tangent is secant squared. Of course, though, don't forget the plus c, and that's your answer right there. So integrals, I'm telling you right now, is one of the first steps of getting into these like tricky types of problems. And I know that's something that people don't like hearing. Oh man, math is going to be tricky, but they're fun. I'm telling you, they're fun to do. You come across these problems and you just try, you know, you try stuff out and just to see if they work or not. And if they don't work, you try something else until you come across a way that you can do your integral. So sometimes you'll need U-substitution, sometimes you won't, right? So let's go ahead and here's 2 problems. I'm going to put up a pair deck, and I want to see your answers on the pair deck for these 2 problems here, okay? So the first example is going to be the integral of 14 over the cube root of 3x plus 1 dx. So we're going to try that one right there. And then number 2, if that's too easy, I want you guys to try this one, the integral of 1 over sine squared x dx. So these are the 2 problems right here. I'm going to set up your pair deck right now. So if you guys could be so kind to click on the link, or you can try working on it right now on your own paper, but I want the answer for your work here on this pair deck. So give me 1 second here while I load this pair deck up. Boop. Let me get the pair deck going. Come on, pair deck. Load it up. I'm going to give you the link. Here we go. Boop. Of course, you can always go to joinpd.com. You can do this on your phone if you want. You could. I really wish Pair Deck would allow you to take pictures. I don't think it does yet, but hopefully soon. PNNBRI. Boom. There we go. What is going on? Uh-oh. Hold up. Oh no, I crashed my Pear Deck. Oh, come on, buddy. Ah, technology. Oh. Okay, hold up a second. Can you guys still hear me right now, or is all of my Chrome crashed right now? We can hear you. Oh, the chat still works. Interesting. Hold up a second. Hmm. I'm not gonna lie to you guys. I don't know what to click on right now. No, it's not that. All right, I'm gonna have to force close this, and we'll lose all my stuff here. But all right, give me 1 second. I'll be right back. All right, can you guys hear me? Okay. Is this working or is it not working? Yes. All right. It also says that my other character is still in here, but clearly I'm in here. Oh my goodness. Okay, let's. There it goes. It says he left. Okay. Okay, so work on this problem. Some of you guys are already on the Pear Deck. Let me go Let me go try this again. And this is still recording. Okay. This will work. This will work, right? This should work. Sessions. This one is live. Okay. There we go. Can you guys do you guys see a blank screen right now on the Pear Deck? It says that there's 9 of you in here. All right, does it still work? Pear Deck has another problem on it. Oh no, yeah. So did it switch over now? It should have switched over to a blank page. No, it's blank now. Perfect. Okay, that was my fault. I'm sorry, but it works now. Ha 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 ha. Nothing bad happened. Nothing bad happened. It all worked out. Ha 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 ha. Sorry about that. Okay, what am I doing here? How do I get the link? Okay. Oh, well, let me just type out the join code again. I can't get the link for you to click and join, but I can give you this link. Oh, thank you. Perfect, David. Lifesaver. There we go. Awesome. Oh, so. All right. David was kind enough to help me out there with getting those links. You don't have to copy down the whole problem. I just want to know what you get as your answers. So try these 2 out. Some of you guys might be able to do number 2 very easily, right? We just did a problem like it. that being said, I should close this out. There we go. Okay. Oh, rough start, rough start. Let me see some answers. Let me see some answers. You guys are still working on there. Let's go ahead and set up a timer for this. Let's go with 4 more minutes for you to try this out. I want to see where you're at. I want to see your attempts. I want to see you try your best. I like what I see for number 2 there, Brian. That's good. Brian B. Monica, I'm liking what I see for number 1. Don't forget to write the integral with it. Looks like you're still on the integral step, so that looks good. Oh, and your number 2 looks good. Good, good, good. David, looking good for number 1. Almost there, I think. You're almost done. Let's see it out, guys. Come on. Try your best. Oh, excuse me. Keep yawning. Oh. Yeah, that looks good for number 1. Monica, that looks good. Ooh, Joe, beautiful on number 2. Looking good. Brian N, very good on number 2. Raheesh, very good on number 2. Beautiful, beautiful. Oh, so nice to see it. So nice to see it. See if we can get a couple more before the timer ends, and if not, that's okay. You guys can still get in there. You guys ever like pop your hip? I sound old saying that. You know how you can crack your back? You ever like get in the right position and get your hip to pop? Feels amazing. All the time? Oop, there we go on the timer. All the time, Monica? Can't get it all the time. I wish I could pop it all the time, but it feels good. Feels good. All right. Let's take a look at this. Most of you guys were able to see that number 2 does not require, right? It happens without you trying. Ooh. Well, as long as it's not painful, I guess, right? As long as it feels good. Sounds painful if it happens all the time, but Or maybe it just is amazing. Anyways, it looks like most of you caught on that number 2 is not one that you need U-substitution for, right? It's not one that you need U-substitution. You could just try and rewrite it and see if you can do it another way, right? 1 over sine is the same thing as cosecant squared x dx. And some of you guys caught on, right? That is a integral that you should know, right? It is one of those basic integrals that you should know. Cosecant squared is going to be the derivative of cotangent x. But remember, when you do the derivative of cotangent, it comes out as negative cosecant squared. So in order to offset that, we put a negative sign in front of that cotangent x. And this is, of course, plus c because there's no numbers on those integrals. And I'm done right there. All right, you're done right there. So that's your answer. All right, that's good to go. Now, for number 1, though, this one I can't integrate. I look at this thing. I don't know what the integral of 1 over that cubic is, and I have some stuff inside of that cubic. Now you'll say, but knock me, 14 does not look like a derivative of 3x. And I'll say it's not a perfect derivative, but it's a factor of its derivative, right? And you'll say, how do you know that? I don't actually. I just try it, right? Like I can't tell you enough that when you do these types of problems, sometimes it's just best just to go in there and try it. I can't rewrite this. It doesn't look like something I can rewrite it into. So I'm going to go ahead and try and let u equal to 3x plus 1. Let u equal to 3x plus 1. And when I let u equal to 3x plus 1, I end up with du equaling to 3 dx. 3 dx. Solve for dx by dividing both sides by 3. And you end up with du over 3 is equal to dx. And that dx is going to replace that dx right there. And of course, the 3x plus 1 is going to be replaced by u. So I'm going to rewrite this here. This is going to be the integral of 14 over the cube root of u times du over 3. Now you'll say, knock me, there's nothing that cancels out here. And I'll say, yeah, that's fine. Because if you remember what my advice was, is that you want these problems, just like your life, to have no x's in there, right? And if you look at it right now, with that substitution done, there are no x's to deal with. And that's going to be a nice problem to work with. So I have here some coefficients. I'm going to write them next to each other, right? So I'm going to write this as the integral of 14 over 3, right, times the cube root of u, which is going to be u to the 1/3. But of course, it's in the bottom, so I'm going to write that as negative u to the negative 1/3 du. I've done a little bit of voodoo magic here, it looks like, but it helps us out because once you rewrite it, right, it's going to be a little bit easier to deal with. I'm going to go ahead and now take the integral of this, rewrite this with the coefficient in front. This will be u to the negative 1/3 du. And we'll end up here with 14 over 3 times the antiderivative of u to the 1/3, right? This is 1/3. Where'd I get the 3 from? Oh, and then never mind, you got it? Okay, hopefully you got it. Please ask some questions if you guys are getting lost along the way. Let me know. I'm going to use the power rule here. 1/3 plus 1 is going to give me 2/3 right here. And then that 2/3, when you simplify that out, when you divide by 2/3, this becomes 3 over 2 as our power in front plus c, right? If you have trouble seeing how I got from here to here, let me know, because I kind of just shortcutted that real quick. Does anyone need to see how I got the integral of u to the negative? I'm just going to show it. I don't know why I asked. I'm just going to show it anyways. Integral of u to the negative 1/3 du is the power rule, which means it's going to be u to the negative 1/3 plus 1 divided by negative 1/3 plus 1. Negative 1/3 plus 1 is going to be the same thing as 3 over 3 right here, which is going to give me u to the 2/3 divided by, same thing in the bottom here, 2/3. The 2/3 in the bottom, when you simplify a fraction over a fraction like this gets flipped and brought up to the top as 3 over 2, u to the 2/3. That's how I got that right there. Hopefully that makes a little bit more sense. The 14 over 3, I'm hoping you guys are able to see. I kind of rushed that as well. The 14 and 3 are fractions that are being multiplied together. I'm putting that as a coefficient in front just because there's no x's, or there's no u's, there's no other pluses or minuses with it. I put that on the front on its own. So when I do the integral, I don't have to really worry about this coefficient. I just multiply by the coefficient once I've done the integral. Now I distribute here and here. 14 and 2 are going to reduce down to 7. The 3 and the 3 right there is going to cancel each other out. I'm going to be left with 7u to the 2/3 plus 14 over 3c, which is just a c right there. We're almost done. We're almost done. U was equal to 3x plus 1. So this is almost done. So 7 times, instead of u, I'll write this as 3x plus 1 to the power of 2 over 3 plus c. And that's my final answer. That's it. It looks weird after I go through all the motions and whatnot to do all this, but yeah, it's a strange one, but that's all U-substitution is in a nutshell. You kind of get through these techniques there and then just kind of take these integrals as they come along and hope that it works out. And I haven't shown you all of them yet. There's some of them where U-substitution takes a little bit more effort than others. And we're going to do more of that later. But for right now, are you guys okay with the basics of this U-substitution method? And I'm going to give you guys some homework problems to try out, to practice this, to see if you are. And if you are, there's a couple problems on the homework that also includes a little bit more higher steps to deal with. Okay? But that's for next time. I'll put that up next time. Today, I want to actually get into this next lesson right here, which is what I should have started this lesson off with, but I didn't because like I said, I was hoping to have made a video and then have you guys watch it on your own time, because it's still a part of the AP exam. It's just not a big part of it. It builds on it conceptually, but the math process behind it is not that big of a deal. But I should have just showed it first. I just didn't realize I was going to be giving you so much work on Khan Academy on that first assignment. Hopefully you guys get that time to do that, because like I'm saying, I'm putting that time aside just so you guys can get onto that Khan Academy, and I really want you to boost that test score up if you're not happy with it. Watch those Khan Academy videos and do those problems, and then I will help boost up your grade even more so with on top of the curve that's there. I don't know if you guys have caught on yet. I'm trying my darndest to give you these points. Take advantage of them. Don't come to me and like don't come to me on like June 5th and just be like, what can I do for extra credit? I'm telling you right now that this very moment you have stuff that you can do for extra credit. So hopefully you're on top of that and you're not going to wait till the very end. Not that, not that you would, or would you? We'll see. All right. Anyways, let's take a look at these slope field problems. Leave the pair deck open, because the first pair deck question is actually going to be where we start off on this one right here. So let's take a look here. Give me 1 second here. Oh, neat. Oh, all right. Anyways, I digress. Let's go ahead and take a look over to slope fields. Right. So, God, hold on. Sorry, I'm like all over the place here. What the? Yeah, that was over here. Why did that go over? All right. So let's take a look at these slope fields right here. This is going to be the first example I wanted to show you guys. It is already on your pair deck. I need that copy actually. Give me 1 second here. Give me 1 second. Maybe we can do this quickly. Come on, knock me the edit to it. There we go. Okay, so let's take a look at this problem right here. And here's how slope fields will work. Whoa. Let's make that a little bit smaller there. There we go. So let's take a look at this one right here. You guys have the pair deck open, right? Hopefully. And it's the same problem that's there. You can also copy this into your notes, or you can just do it on the pair deck and take a screenshot of it and print it out and put it in your notes. But here's the idea here, right? I have a function here. Y is equal to 0.5x to the second. Can you guys help me out here? What's the derivative of that? What is the derivative of y is equal to 0.5 x squared. What would that be? What would that derivative be? All right, what would dy dx look like? It would just be x. Very good. It would be 0.5 times 2, which would just be 1 times x. So it would just be x. So the derivative would just look like this, right? It's just equal to x. You guys okay with that? Right, hopefully. Now, check this out. At each grid point, you see all the dots here? These are all little grid points here. So this grid point right here would be -1, 4, right? You see that? It goes to -1 on the x-axis and it goes up to 4. And there's a bunch of grid points all around here, right? There's a grid point over here. This would be like 4, 0, right? At this point right here, right? And this one over here would be like -4, 0. That's right here, right? This one right here would be 0, 4. And there's just a bunch of them all the way around there, right? What I'm going to do right now is calculate the value of the derivative for each of those points and draw a short line segment with that slope. You're saying, what, Knockme? What are you doing? So check this out. So let's take a look at this point right here. What point is this that I just drew a dot at? What is that point? Can somebody tell me? That origin there. What's the coordinates of that origin? Monica is saying that is 0, 0. So I'm gonna put this off. This is gonna be my work over here. You guys don't need to write this on the Pear Deck, by the way. That's just easier, like for you to see and then make a copy of. But right here, at 0, 0, I'm gonna plug that into the derivative and see what is the value of the slope of the tangent line at that point, right? What's the slope of the tangent line at that point? So at 0, 0, I'm gonna plug that into the derivative, right? So I have here the derivative, or the slope at that point, is gonna equal to 0, right? Because that's the x value I plug in for x. So at this particular point right here, I'm gonna draw a line segment with that slope, and that line segment will look something like this. See that? It's gonna happen to be right there at that point. So I'm gonna just draw it through that point, actually. I'm gonna just draw it through that point, like so. And there's my short line segment. Right, there's my short line segment. I'm gonna do it again. Let's do the point right below it. The point right below it is this point right here. That's gonna be the point 0, -1. If I plug that into the derivative, what would I get there? What would I get there? What would I get when I plug in 0, -1 into this derivative? Well, the derivative only has an x value, and I'm only gonna look at this x value right here. That x value is gonna be 0. So guess what that's gonna look like? That's going to look like this as well. It's going to have the same line segment because it has the same slope. And that's actually going to be the case for all of these values of x equaling to 0, including, right, 0, -2, 0, -3. All of these are going to have an x value of 0, so they're going to have a slope of 0. So all of these are going to have slope values that look like this, including up here. So these are, you don't have to make them that long, by the way. They're like little short segments here, right? And these are all the slopes at these particular points, right? At 0, 4 has a slope of 0. At 0, 3, it has a slope of 0. At 0, 2 has a slope of 0. Are all these dots going to have a slope of 0? Like, for example, if I pick a random dot, and let's say I pick a random dot right here, for example, this dot right here. That dot right there is 2, 0. What do you guys think about that one? Is that going to have the same slope? Is that going to have the same slope as all the other ones? And Monica's saying, nope, nope. Since the equation for your derivative is equal to x, then dy dx at 2, 0 is going to equal to 2. Then it's going to equal to 2. And what does that look like? Do you guys know what the slope of 2 looks like? What does the slope of 2 look like, by the way? It looks like it's supposed to go up to 1, 2, and over 1. So it's going to look something like this, isn't it? It's terrible, not going to do a better job. It's going to look something like this. You see that? And that's actually going to be the case for all the values of x equaling to 2 because of, well, our derivative being equal to this, right? Since our derivative is equal to this, the other place that this will happen at is also at 2, 1, 2, 2, 2, 3. All of these, right, the dy dx the derivative is going to equal to 2 for all of them because we're just looking at the x values, right? And how did I get this equation, by the way? I got this equation by taking the derivative of this. Keep that in mind. I got this equation by taking the derivative of this. So when I do that, I come over here, and I have here, this is going to be a slope of 2 as well. So this line right here is going to be the same as that line. I'm going to cheat a little bit here. Can I cheat? Will it let me cheat? No? Will you not let me cheat? I don't want to. Oh, wait. I got you. Nope, it's not going to let me do it. All right, it doesn't matter. I'm just going to go ahead and draw it out. So they're all going to look like this, right? They're all going to look like this. Huh. You guys notice anything when I drew it right here on my line right there? What do you guys notice when I drew it right there? I drew this slope all the way through for all of these. What do you notice about that slope right there? Hoping that you guys notice it. Doesn't it look like it's a perfect tangent line at that point? Just like at 0, 0, doesn't that look like a perfect tangent line to the function right there? Which makes sense because, well, we're graphing the derivative, right? So all these derivative values should be doing that. So if I were to sit down and I've had more time to do this, I would be doing this for all these x values. So this one right here would be -1, 4, right? And this right here would be a slope of dy over dx equaling to -1. And a slope of -1 would look something like this. And then I do it for -1, -3, -1, -2, -1, 0, -1, 1, -1, 2, and -1, 3. Oh, shoot. Those are not 4s right there. Those are 3s, aren't they? Wait, it goes 4 this way, but it goes 3 up top. Whoops. That's a mistake. It only, right? Because that's 0. And it goes down to -3. Yeesh. Knock me. Yeesh. Anyways, would it create multiple graphs of the function? And Monica's already kind of caught on to the idea here. If I do this for all of them, right, this is what it's going to look like. This is what it's going to look like. So I do this one right here, do this one right here, do this one right here, this one right here. And again, you would be plugging, what you'd be doing to get these values, you would be plugging in the coordinates of your x and y values of these dots into your derivative equation. And when you plug them in, it gives you the slope, right, at that point. And what you do with that slope is you graph it with a little secant line, with a very small secant line. And when you start graphing them, right, this is going to be a little bit steeper here, right here, like so. And then this will be very steep, like so. And then these will be steeper on the negative sides. This would be -2, like this. Boop, 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 boop. And then this would be steeper this way. And again, you would just be plugging them in just to see it. And Monica's already beat me to it. I'm hoping that you can see it. This is pretty much graphing a family of slopes, right? Do you see it? And if you look closely, right, this one right here follows through the slope field. It goes with the curve. The curve there is kind of formed by the slope field that surrounds it. You see that? It kind of forms with that slope field that surrounds it. Now, the family here of graphs here, right? I don't know if you can tell or not, but the family looks something like this, right? The family of this original graph, right, was y is equal to 0.5x squared. 0.5x squared. Okay? With that being said, the only one we really care about is this blue one, but that is the only one we care about is because the initial condition is the one that sets it for us. Is the one that sets this for us. The initial condition, by the way, is when x equals to 0, y equals to 0. It's this dot right here. And they kind of don't really tell it to us right there, but it is our initial condition is the point that goes through that function. And it allows us to, you know, kind of sketch that graph right there. So it's a little weird. It's a little weird, but that's just how that's all a slope field is. It's basically a field that gives you all the possibilities of what your function could be if you know what the derivative values are. and they get kind of weird. You know, they get a little strange, a little funky. But right for right now, we're not going to worry too much about that part of it. We're going to worry about calculating and drawing your slope fields. In the past 3 years, there's been at least one free response per year where they ask students to draw the slope field. Of course, they're not going to ask you to do this many, though. This is 1, 2, 3, 4, 5, 6, 7, 8, 9 times 1, 2, 3, 4, 5, 6, 7. This is like 63 slope fields we had to draw here. 63 tangent lines we had to draw. That's a lot. Most of the times on your AP exam and on my exam, you'll have to draw about 6 to 10 slope fields or tangent lines in one slope field. So this was kind of an over-exaggeration, but when you do something like this, it makes it easier to see it as a whole. When you only draw like 6 of them, it doesn't really show you the overall what it looks like, but you know, it's just something that if you do too many, it just takes too much time. So they only ask for about, like I said, 6 to 10 usually on the exam. The other thing that they might tend to do is they might give you the slope field fully drawn out, and you have to kind of guess at what the function kind of looks like based off of that. I'm going to give you one example right now. If I give you this example right here, not on the Pear Deck, just take a look over here. If I gave you a slope field, right, right there, excuse me, can you guys see that that slope field has multiple possible graphs? Right, I have a green graph there, red graph, blue, orange, and purple. All of these fit with the slope field that's there. And if I were to look at this, could you guys tell me, what do you guys think the parent function is for this graph? What do you guys think would be the parent function? Well, yeah, well, that's the, for all of them, I should say, Monica, for all of them. Probably not y is equal to 0.5x, right? 0.5x is going to be something like that, right? And that doesn't follow that slope field, right? X squared is the parent function, right? Y is equal to x squared. And all of these are different x squareds, right? Like this one right here would be x squared plus 1, that one in blue right there, right? This one down here would be x squared minus 1, 2, 3, 4, 5, 6, 7, right? This one up here would be x squared plus 9, for example, right? They're all x squared graphs, but x squared plus something. You see that? And they all fit into here, like x squared minus 3, x squared plus 1. That's where the idea comes into play, that once you have the parent function, the graph itself is just some function plus a constant. And that constant is the one that tells you, oh, it's this particular graph. No, it's this one over here. No, it's this one. No, it's this one. That's what that C comes into play. It's going to help you and catch in the idea that when you have a slope field like this, it can be any one of these, right? It can be any one of these. And we figure out what that C is by only if the problem tells us a initial condition. So usually the initial condition is very straightforward, and they'll say like, oh, initial condition is that it needs to pass through the point 0, 1. And that 0, 1 would be this point right here. And then your graph that you only want to focus on is that blue graph, right? You don't want to focus on any of the other ones if they give you an initial condition. If they don't give you an initial condition, it could be any one of these, right? It could be any one of these on those slope fields there. Okay. With that, all right, there is one more I want you to try on creating these slope fields. So give me 1 second here. Here, try this one out. I'm going to put this over here, and I'll start it off, and then you guys can finish this off on your own and put this into your notes. So give me 1 second here. Let's copy you, put you down like so. There we go. And I'm going to close you and then reopen this because you're lagging very hard, so I can't really change the color. So let's try this again. So let's take a look at this one, right? I got a couple minutes here. Notice the differential equation that we're dealing with has both an x value and a y value. You ready? So I can't actually test 0, 0. I hope you guys can see that, right? If I test 0, 0, right? Remember, this is my x and y value that I'm going to be testing, 0, x comma y. I'm going to be testing into here. And the equation is dy dx is equal to negative x over 2y. So what they've essentially done is they've taken the derivative of a function. I don't know what the original function is, but they took the derivative and they got negative x over 2y. So it's clearly something that is implicit. It's not an explicit form. It's not only in the form of x's. It has x's and y's. So what I'm going to do right now is I'm going to calculate the slope at some points along the way. So I'm going to look at this point right here. This point right here is 1, 0. 1, 0. What type of slope do you have at 1, 0? dy dx is going to equal to negative 1 over 2 times 0, which is going to give me negative 1 over 0, which is undefined. Undefined. So I don't really have a slope there. That's not a good point. Let's try another point. Let's try this point up here. That point up there is 1, 1. Let's see what that derivative looks like. dy dx is going to equal to negative x, which is going to be 1, over 2 times y, which is 1. So this is going to give me a slope of negative 1 over 2. So at this point right here, I have a slope of negative 1 over 2. So it's going to look something like that. Oh, let me try that again. It's going to look something like that. So I've gotten that one right there. Pick another point. Someone pick a random point for me. Anybody. Name a random point that you guys see on there. Give me a point. 3, negative 4. Negative 3. Wait, 3, negative 4. That's off the chart. That's off the chart, Monica. We don't need to do that one. 3 is too far. This one goes from 1 to, this goes 0, 1, 2. So make it a little bit smaller for me. Make it a little bit smaller for me, Monica. The x-axis goes from negative 2 to 2. The y-axis goes from negative 2 to 2 as well. So make it in that box, somewhere between negative 2 and 2. All right, so Monica's going with 2, negative 2. Do you guys see where that is? 2 is right there, negative 2. That's this point right here. I'm going to go ahead and calculate that slope. dy dx is equal to negative x, right? Negative x over 2 times y. In this case, y is equal to negative 2. So this right here is going to give me negative 2 over negative 4. The slope at that point is equal to negative 2 over negative 4, or 1 over 2. 1 over 2. 1 over 2 looks something like, it's going to look something like that. Something like that right there. You don't have to do these in different colors or anything like that, but here's what I want you to do. Fill out the rest of these dots with those tangent lines that I have drawn there. Make your slope field for this problem for me. That's going to be what I want you to do for your homework. Leave this pear deck open. Finish this off, and that's going to be your homework assignment for you guys to have done. I'm going to take a look at this next time we come back, and I want to make sure and see what we have as our answer and what our slope field is going to look like. Okay? If you get something that's undefined, for right now, just leave it alone. Leave it alone. It's going to be undefined for all of these points right here. It's going to be undefined here, undefined here, undefined here, and undefined here. We're just going to leave those alone for right now. So take a copy of this, fill out the rest of these, and that's going to be the only homework for right now because, like I said, I want you guys to have some time to do that extra credit on Khan Academy. Okay? All right, with that being said, I'm going to stop here. We'll continue on with this on Thursday. Yeah, and if you have any questions, stop by during office hours today from 1 to 2. All right, other than that, I'll see y'all on Thursday. Have a good rest of your day, guys. So long, farewell, sayonara. Bye, everybody.